We're going to look at the vector equation of a line rather than just the equation of a line. First of all, we'll just look at a two-dimensional situation. So there's our coordinate plane, and we've got this red vector there. We want to find its equation. R is just representing some random points on the line. And so it'll have a position vector of R. A and B are 2 points that we know are on the line, and they would have position vectors of A and B. So R is lying on this line AB. So then what we know is the vector AR must be some multiple of the vector AB, because they're travelling in the same direction. It's just that their lengths are different. So that must be true. All right, well, let's play around with that. We know vectors are head minus tail. So R minus A will equal some multiple of B minus A. But remember, we're trying to find an equation for R. So R would be A plus some multiple of whatever B minus A is. That is what we call a vector equation of a line. Let's just prove that that is indeed going to give us the equation of a straight line. So let's give A and B some coordinates. There they are. And then we'll write them as column vectors. So R is some random point. So the column vector would be x, y. We're saying A ends up being x1, y1 times some multiple, and then the difference between B and A. So x2 minus x1 on y2 minus y1. So basically what we've now got are parametric coordinates for x and y, the parameter being lambda in this case. Well, what that means is that both, if I play around with the first one, x minus x1 and x2 minus x1, and if I play around with the second one, y minus y1 and y2 minus y1, they're both equal to the parameter, lambda. That actually is the Cartesian equation of a line. You just don't recognise it as that because you're not used to seeing it written that way. Don't worry about the lambda, I'll just focus on the first two. Look what happens. If I cross multiply, expand out, we end up with y minus y1 equals m outside of x minus x1, which we recognise to be the point slope formula. So yes, that vector equation of a line does in fact produce what we recognise to be the equation of a line. Alright, well, so how can I write the vector equation of a line, not the equation of a line, the vector equation of a line passing through these 2 points? What do I do? Well, I write it down. Simple as that. Whoa! Remember, we said it was some point that is on the line. Well, 3 minus 5 is on the line. Lambda times the difference in the two, because you're basically saying head minus tail. So I've just subtracted the x values. Difference is, be careful, because slope we normally put y on top, but we're writing column vectors, so the x goes on top. So difference in the x values, difference in the y values, plus or minus, it doesn't matter because we're multiplying it by lambda. Now lambda could be a negative number, so it doesn't matter. I could have written it that way. I could have easily chose the other point, minus 2 minus 8. It would be the same equation. So that's all you have to do. The actual Cartesian equation ends up being that. Now, why is that important? Just have a look at the similarity between the slope and that vector there. That vector there is what we call the direction vector. So it's the direction that the vector is actually travelling in. The only difference is it's like upside down, if you like. Some other ideas. Remember in complex numbers we said rotation 90 degrees, multiplication by I. Run over rise, because our direction vector has the x on top and the y. So instead of saying rise over run, the column vector would be run over rise. If I multiply that by I, then I get run plus I rise times I. Well, that becomes I run minus rise. Does that mean I fall down after I've run? Anyway. So I end up with minus rise over run. Multiplication by I, what has happened? 90 degrees, negative inverse. I just thought that was interesting. Okay, so what we've just proven is that in fact these are perpendicular. But of course we knew that anyway, because with the dot product I could have just said, oh well yeah, well if I multiply those I get 0, and if they multiply together to give 0, they must be perpendicular. Okay, let's go back to vector equations. There's the Cartesian equation of the line. What is the vector equation for the line? Again, I'll just write it down. I can pick any point I like that's on that line. For some reason I chose negative 2, 1. You pick anything you like, and then what's the slope of that line? Oh, the slope of that line's minus 2/5. So I just sort of turn it upside down. That becomes the direction vector, 5, negative 2. Find the point of intersection of two lines. So we now have another way we can do this, but using vectors. Because I can say, well, that first line, pick any point on the line. I've gone 0, negative 1. The slope of that one's negative 2, so the direction vector is 1, negative 2. There's the vector equation of that line. There's the vector equation of the other line. Notice I've used a different scalar multiple there. I've used mu rather than lambda because there's nothing to say those numbers will be the same. All right, so looking at the first one, we know that lambda, I'm just looking at the x values, and then in the second one is equal to 3 plus 5 mu because we want the point of intersection, so they've got to be the same. When I look at the y ones, I get minus 1 minus 2 lambda is equal to minus 3 mu. So I'm still going to end up using simultaneous equations. But the difference is I only need to find one of them. I don't need to find both of them. Because as soon as I know one of them, there's mu equals negative 1, I can substitute in and I've got the point, because the point will be when mu is equal to negative 1, add across, and we've got it as negative 2, 3. An alternative way of finding simultaneous equations. We're going to find the vector equation that joins these 2 points. We're then going to write the parametric equations for any point, and from that we're going to work out where that line meets the parabola y equals x squared. Well, the vector equation, that's the easy bit because I can pick any point. I'm using minus 1, 1. Difference in the values, so I've gone, where are we? Hang on. 4 minus minus 1, that's not 1. 11 minus 1, that's not 2. What have I done? Yeah, I had a common factor of 5. So because lambda is any multiple I like, then I've just simplified it down. So if there's a common factor in the numbers, I can make it even easier. So it's still the same direction vector. Yeah, I should have got 5, 10 when I did that. And it's still not wrong. I mean, if you put 5, 10, it's still right. It's the same direction vector. All right, so from that, we now know x is minus 1 plus lambda, y is 1 plus 2 lambda. There's the parametric equations for any point on that line. We want to know when y is equal to x squared. So I'll sub in the parametrics. Let's find when that happens. We have to solve this quadratic, and we get 2 possibilities. So this line must cut our parabola twice. Sub in 0 for lambda, and I get minus 1, 1. Sub in 4 for lambda, and I get 3, 9. So I found where the line meets the parabola. All right, so that's 2 dimensions. What happens when we start thinking about 3 dimensions? Equation of a line? Look, it does not matter how many dimensions you got, that's always going to be true. The line will be some vector that we know plus a multiple of the direction vector. That will always be true. So A is any point, B is our direction vector. Okay, so how will I find this one? There it is. Any point I like on the line, 1, 2, 3. How do I do the direction vector? Head minus tail. So x values, which way round did I go? I went the first one minus the second one. So 1 minus minus 2 gives me 3. 2 minus 7 is negative 5. 3 minus 4 is negative 1. I've got a direction vector. So it's exactly the same idea. The difference here is we can't say, oh, it looks like the slope upside down because I've got 3 numbers and it doesn't kind of make sense anymore. So what would the Cartesian equation be? Cartesian equation. Well, that's my Cartesian equation. There's 2 equal signs? Yeah, we're in 3 dimensions now. But think back to when we did 2 dimensions. What we basically said was, oh, both these things were equal to lambda. Now in 2 dimensions, when we're doing our Cartesian geometry, we don't normally write equals lambda down. The reality is there is still this equal lambda there. I haven't written the equals lambda down here either. But essentially what I've done is I've just read across the line and made lambda the subject. So x was equal to 1 plus 3 lambda. Rearrange that, I get lambda is x minus 1 on 3. The second line, Y is 2 minus 5 lambda. Rearrange that, lambda is 2 minus y on 5. And then finally Z is 3 minus lambda. Rearrange that, I get lambda is 3 minus Z. So all these things are equal. Let's look at some HSC questions now that we've had a couple of HSCs in this new course. So the very first one, 2020. We've been given two lines. By equating components, we're going to find the point of intersection of these two lines. Okay. If they're going to intersect, the x values have to be the same. So 3 plus lambda 1 is equal to 3 minus 2 lambda 2. Play around with that. I know lambda 1 has to equal minus twice lambda 2. Now I'll look at the y values. Minus 1 plus 2 lambda 1 is going to be the same as minus 6 plus lambda 2. But we just said lambda 1 was minus 2 lambda 2, so I can substitute that in. I've now got the value for lambda 2. Hang on, I already know what's going on. I'm going to do the z values, and I'll explain why in a second. 7 plus lambda 1 is equal to 2 plus 3 lambda 2, but we know lambda 1 is minus 2 lambda 2. Oh, look at that. Lambda 2 is equal to 1, which we already knew. Why did I do that? You see, in 3 dimensions, it's unlike 2 dimensions. In 2 dimensions, unless the lines are parallel, of course, the lines will always meet. The same is not true in 3 dimensions. You can have lines that are not parallel, and they won't meet because of just which plane they might be sitting on and things like that. So we have to confirm that, yeah, they do give us the same value, so these lines are in fact intersecting. Now actually, the reality is for this HSC question, you wouldn't have had to do that, because in the question you were told, or it's sort of implied, that yes, they do meet, because they've said find the point of intersection. So you probably wouldn't have to do that for this one. But reality is, if you want to find whether things meet, you need to check this. So all right, we now have to actually find the point of intersection. I can substitute in, well, lambda 2 or lambda 1. Which one did I do? I substituted in lambda 2 into the second one, add across, and we've got our point. There it is, 1 minus 5, 5. Oh, I wrote it as a column vector. I probably should have written it, because they asked for the point, I probably should have written it as 1 minus 5, 5. Find the vector equation of the line that passes through this point but is parallel to this vector. So now, we usually say they're parallel if their slopes are the same. But that's a 2-dimensional idea. In 3 dimensions, we say 2 lines are parallel if their direction vectors are scalar multiples. So they don't have to be identical. As long as one's the multiple of the other, then we know they're going to be parallel. Okay. Well, I can now write down my equation. A point that's on the line, minus 2, 1, 4, I've just got to write down the direction vector. Well, it's parallel to 2i plus j minus 2k, so it's going in the same direction. So that's my direction vector, 2, 1, negative 2. There's the equation of the line. What about if they're perpendicular rather than parallel? Okay, this one takes a little bit more work, but we remember 2 lines are perpendicular if their dot products is 0. So I'm going to call the direction vector I'm looking for ABC. It's not as easy as simply saying O negative inverse like we do in 2 dimensions. So I'm going to say this dot product has to equal 0. So A minus B plus 4C must have to equal 0. I know that. But here's the other thing. They have to intersect. To be perpendicular, they've got to actually touch. So that's the other bit of information we know. They have a point of intersection. So there's my equation of the line there, 0, 2, 3, and direction vector ABC that I don't know, but it has to equal the other one. So I'm saying it's some scalar multiple of 1 minus 1, 4. All right, that brings us up with 3 equations here. I can play around with them. I get in the first one there, lambda is minus 2 on A plus B, and the second one there, I've got 3 on 4A minus C. Okay, they've got to be equal, so I now come up with this equation. 11A plus 3B minus 2C is equal to 0. So I know that has to be true. Well, solve them simultaneously. The other one was, what was the other one again? There it is, a minus b plus 4c. So I've multiplied everything by 11, so I can eliminate the 11 a's. That gives me that b is 23c on 7. Now I can pick any number I like. So to make the maths easy, I've made c equals 7. So if c equals 7, b is 23, a is negative 5, I now have my direction vector. It's a little bit more work to do for a perpendicular question than is a parallel question. So keep this in mind. This is what I was just saying. Two lines have direction vectors b1 and b2. They're going to be parallel if one is a multiple of the other. They'll be perpendicular if their dot product is equal to 0 and the lines intersect. Other situation we've got is they would be skew. The lines would simply say skew. They're not parallel and they don't intersect. So that's the third option we might have. So we're going to show that these two lines are indeed skewed lines. Basically, we have to show there's no point of intersection. 1 plus lambda equals mu. 3 plus lambda is 4 mu, minus 1 equals 5 mu. If there is a solution to this, then we know they're going to intersect. That's not what we want. So if I equate 1 and 3, looking at 1 and 3, I get mu is equal to minus 1/5, that's the third one. Sub that in, I get lambda is minus 6 on 5. If I equate 2 and 3, I end up with lambda is minus 19 on 5. So it does not equal minus 6 on 5. So they do not intersect, but remember the other key thing is they're not parallel, but we can easily look at the direction vectors and we can see one is not a multiple of the other. So we know they're not parallel. So third option, they must be skewed lines. Okay. Ooh, that was a bit, wasn't it?